Hi everyone, today I'm going to talk about breaking certifiable defenses. At first, I'd like to talk about the adversarial machine learning. Let's say that we have a binary classification task, like classifying images of a cat and some other class, say a black swan. The goal of the adversary is to add a very small noise to the image so that it gets classified as a different label, while it remains the same to the human eye. There are many different types of attacks and many different types of defenses. Over the past few years, different people have published papers about different ways to attack deep neural networks or different ways to defend against these attacks. Going back and forth, sometimes a new attack is so strong it breaks all of the previously known defenses, and sometimes a defense is so strong so that it survives all of the previously known attacks. So if as the adversary we're trying to break a new defense, and we fail to find adversarial examples, maybe it's not because there are no adversarial examples. Maybe there are some, but it's just too difficult to find them. To address this, people have proposed the certifiable defenses. Certifiable defenses generate a certificate for the prediction that they are making. For instance, here the network is saying that this image belongs to the black swan class with probability 91%, and also there are no adversarial examples within a distance of 1.2 around this image. And by distance, I mean in an LP norm distance metric. For instance, here we're using the L2 norm. So the question that we're asking in this paper is how good the certificate radii is as a measure for robustness. Because intuitively, some might think that when the certificate radii are larger, it's safer to trust the network's predictions. I would like to emphasize that none of the certifiable defense papers make that claim, and that's not even the purpose of the certifiable defenses in the first place. We're just saying that one should not confuse the size of the certificate radii as a measure of robustness. To address this, we show that we can find adversarial examples that have three properties. They are natural looking, the prediction of the network for them is wrong, and the certificate radii for them is huge. The third property is really important to us because if someone does trust the network's predictions when the certificate radii are huge, then they should trust the network's predictions for such adversarial examples as well. So now let's say that we want to attack a certifiable defense. What should we do? If we keep the perturbation to be small, then the example remains close to the original image. In other words, it remains close to the decision boundary. And because of that, the certificate radius would be small. However, if we moved further away from the original image, then we would find adversarial examples with huge certificate radii. So to do that, we propose the shadow attack. We'd like to call it the shadow attack because the adversarial noise doesn't change the color of the pixels, and instead, it makes some of them lighter or darker. So it's kind of like you have a natural image and you put some shadow on it, and all of a sudden, it gets misclassified as a different label. So this is the loss function for the shadow attack. As always, the first term is the classification loss. The second one is a color regularizer to make sure we don't change the brightness or darkness of any individual pixels too much. The third term is to make sure that the added noise is smooth and it doesn't have any visible edges. The last one is to make sure that we add the same amount of noise to the RGB channels at the same time so that it doesn't change the color of the pixels as opposed to making them lighter or darker. So in this paper, we attack two different certifiable defenses. For the L2 norm, we attacked the randomized smoothing by Cohen et al. In 2019. And for the L-infinity norm, we attacked the crown-IBP by Zhang et al. In 2020. So at first, I'm going to talk about the randomized smoothing. In randomized smoothing, we use a mini batch of randomly chosen small noises and add them to the original image. Then the network does predict the labels for each of them independently. Then we take the majority vote of the predictions to get the prediction of the network as a whole. Also, the more the predictions agree with each other, the larger the certificate radii will be at the end. So to attack this method, we just need to find a perturbation that changes most of the votes to the target label. And since most of them agree on the same target label, then the certificate radius will be huge. So here are our results for attacking the models from the randomized smoothing paper for ImageNet and CIFAR10 datasets. And as you can see, the average certificate radii is even larger for the adversarial examples compared to the natural images. The second method that we attack is the crown-IBP by Zhang et al. In 2020. In their method, there's a term in their loss function that reflects the size of the certificate radii. So to attack this method, one just needs to optimize over that term to make sure that the certificate radii is also huge for the target class. Also, here we're showing the success rate for the attack and the defense just to be comparable with the tables that they have in the crown-IBP paper. So as you can see, most of the time, the success rate of the shadow attack is more than the crown-IBP defense. We hope that you have enjoyed this presentation. Thank you for your time.